Hello, and welcome to B26's presentation of universal and existential generalization. So, universal generalization is defined as a rule of inference for quantified statements that states that if a predicate P of C is true for an arbitrary C, then for all x, Px is true. This can be written as this statement right here, which translates to P of C for arbitrary C, therefore for all x, P of x is true. This is a logical inference that allows one to move from an arbitrary and non-specific statement to a quantified generalized statement.
Alright, for our first example, we let P of x denote x is wearing a blue shirt, and we say x is the domain people in the room. If P of C is true for an arbitrary value C in the domain x, we can say for any person in the room, that person is wearing a blue shirt.
In our second example, we want to ask what rules of inference are used in this following proof. And so we're going to say for any person who works at Taco Bell, that person likes tacos. Then all who work at Taco Bell like tacos. If P of x denotes x works at Taco Bell, and Q of x denotes x likes tacos, and the domain of C are people who work at Taco Bell, then our premises are if P of x, then Q of x for any x, and we use this domain C of all people who work at Taco Bell, will make P of x true. So we have this second premise, P of C is always true. So starting out, we'll use our first premise and say if P of x, then Q of x for any x, then we can use a universal generalization and say that for all C, so long as they're in the domain of x, if P of C, then Q of C. Using our second premise, for all C, P of C is true, we can conclude using a modus ponens that because for all C, P of C is true, and for all C, if P of C, then Q of C, we can conclude for all C, Q of C is true, using modus ponens.
So for our next example, we will use rules of inference to show that these two premises then lead to this conclusion being true. So first we use the second premise and universal instantiation to say that P of A and R of A are true. Then we simplify this to just P of A. And using this simplification and the first premise and universal modus ponens, we have Q of A and S of A is true. We then can simplify that to just S of A. And we can simplify the very first statement to just R of A. And then we can use conjunction on statements 4 and 5 so that R of A and S of A are true. And finally, we use universal generalization to say that for all of x, R of x and S of x are true.
Alright, next up is existential generalization, and the definition for that is a rule of inference for quantified statements that states that if a predicate, P of C, is true for one particular C, then there exists some x such that P of x is true. This can also be written as P of C for some element C, therefore there exists x such that P of x. And this is a logical inference that allows one to move from a specific statement to a quantified generalized statement.
Alright, for our next example, on existential generalization, we let P of x denote x is wearing a blue shirt and the domain x be people in the room. In this example, we know that one particular person in the room is wearing a blue shirt. Without needing to know whether the other people in the room are wearing blue shirts or not, we can say that there exists at least one person in the room who is wearing a blue shirt.
And in our last example, we are going to use the rules of inference to prove that if we have these four premises, A, B, C, and D, then we can conclude our conclusion right here. That is, there exists an x such that not R of x is true. So to start out, we take our D premise into an existential instantiation that says because there exists an x such that not P of x is true, we're going to say that P of C is this x that makes not P of x true. And C will be an element of the domain X. And so we'll go and use our A premise now, and because for all x, P of x or Q of x is true, we can replace this x with C and in a universal instantiation that says P of C or Q of C are true. Furthermore, we will combine this first step and the second step in a disjunctive syllogism that says if not P of C and P of C or Q of C, then we can conclude Q of C is true. Taking our B premise over here, that says all of x, not Q of x or S of x, we can also replace x with C because all x make this statement true. And this is universal instantiation that says not Q of C or S of C. Using our third step, Q of C and not Q of C or S of C, we can use a disjunctive syllogism to conclude that S of C is true. Now, finally, we take our C premise, and also, because all x make this statement true, we replace x with C and say that if R of C, then not S of C in universal instantiation. And we use a modus tollens to say that since S of C is true, and R of C, then not S of C is true, we can conclude not R of C is true, leading us to our conclusion that says because this C makes the statement true, not R of C, then there exists an x, not R of x, that is true because C is an element of the domain X.
Thank you for listening and have a nice day.